In this video, we're going to examine some relationships. First, we will need to draw and interpret the explanatory variable and the response variable using the scatter diagram. We will describe the properties of linear correlation coefficient. We will compute and interpret the linear correlation coefficient. We will determine whether a linear relation exists between two variables, and then explain the difference between correlation and causation. The response variable is the variable whose value can be explained by the value of the explanatory or the predictor variable. A scatter diagram is a graph that shows the relationship between quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis, and the response variable is plotted on the vertical axis. Let's look at this example right here. The data shown to the right are based on a study for drilling rocks. The researchers wanted to determine whether the time it takes to drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which the drilling begins is the explanatory variable, which is, we're going to say this is x, and the time measured in minutes is going to be the response variable, which is we called y in this case, and it's measured in feet. We want to draw a scatter diagram for this set of data. So this is how we're going to draw a scatter diagram for our set of data on Excel. So here is my data on Excel. I just copied and pasted here. The first thing is you need to make sure that the explanatory variable is the column to the left and the response variable is the column to the right. So x comes first and then y next. The next step, we're going to select our data and then go to the Insert tab. And then from the Insert tab, you're going to select the Charts section, and you're going to select the scatter plot. So here is the scatter plot. As you can see, the explanatory variable is represented on the x-axis, and the response variable is represented on the y-axis. Add the axis titles if that is something that you're interested in. But this is how we're going to create the scatter diagram. So this is the first step in order to figure out the relationship between two variables. After we plot our relationship between the two variables, you can see a trend in your data. Types of relationship in a scatter diagram could be the linear relationship. The linear relationship, you'll see that the scatter diagram tends to be going in one direction. Either it's going upwards or it's going downwards. If it's going upwards, when you scan it from left to right, that means the relationship is linear and it's positive. If it is going downwards when you scan it from left to right, that means it is linear and it's negative relationship. Positive relationship means when the explanatory variable increases, the response variable increases as well. Negative relationship just means when the explanatory variable increases, the response variable decreases. Some other relationship could be nonlinear. It could take any other shapes. In general, the trend is not going to be moving in one direction. It will be all over the place. Or it could be going in trends like curves, going up and down, or it doesn't even take a shape. So those are called nonlinear. And the last one, that it doesn't take any trend or any shape, is we say that there is no relationship in this case because we can't see a trend in the scatter diagram that we just graphed. Two variables are linearly related, are positively associated when above average values on one variable are associated with above average values of the other variable, and below average values on one variable are associated with below average values of the other variable. That is, two variables are positively associated if whatever the value of one variable increases, the value of the other variable also increases. That's what we call the positive relationship. Two variables are linearly related, are negatively associated when above average values of one variable are associated with below average values of the other variable. That is, two variables are negatively associated if whenever the value of one variable increases, the value of the other variable decreases. And we can see many of these examples in real life if you look closely to the relationship between two variables, a response variable and an explanatory variable. You will see that we have many positive and negative relationship that we can actually study. The linear correlation coefficient is a measure of the strength and the direction of the linear relationship between two quantitative variables. The Greek letter rho, which is this letter right here, represents the population correlation coefficient. Mostly we're going to deal with lowercase r, which is the sample correlation coefficient. And we present only the formula for the sample correlation coefficient in this course. We're not going to study or discuss the population correlation coefficient. So the sample linear correlation coefficient is given with this formula. The formula says the sum of xi minus x bar is basically the sample mean of the explanatory variable divided by s sub x. S sub x is the sample standard deviation of the explanatory variable, times yi minus y bar is the sample mean of the response variable, divided by s sub y. S sub y is the sample standard deviation of the response variable, divided by n minus 1. N is the number of individuals in the sample. Xi here represents each value of the explanatory variable, and yi represents each value in the response variable. We are not going to use the formula, but I will show you an example on how to compute the correlation coefficient by hand. This is not what we're going to do in this course. We're going to compute the correlation coefficient, the sample linear correlation coefficient, using Excel. Here are the properties of the linear correlation coefficient or the sample linear correlation coefficient. The linear correlation coefficient is always going to be between -1 and 1, inclusive of 1 and -1. If r is equal to +1, then a perfect positive linear relation exists between the two variables. If r is equal to -1, then a perfect negative linear relation exists between the two variables. The closer r to +1, the stronger the evidence is of a positive association between the two variables. The closer r is to -1, the stronger the evidence is of a negative association between the two variables. If r is close to 0, then little or no evidence exists of a linear relation between the two variables. So r close to 0 does not imply no relation, just we say we don't have linear relation. The linear correlation coefficient is a unitless measure of association, so the unit of measure of x and y plays no role in the interpretation of r. The correlation coefficient is not resistant, therefore an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. Let's look at some examples of what we just talked about. So the first example here, as you can see, I can tell that the linear relation is perfect and it's positive because I can fit a perfect line along these dots right here. So r is going to be equal to 1 in this case, +1. The next example, B, I can see a trend of dots going upwards, and I can see that this is a strong positive linear relation, so r is going to be approximately 0.9. The next picture right here, C, I see here that the trend is still going upwards, so I can still assume that there is a positive linear relationship. It's a moderate one, so r is about 0.4. In the next picture, D, I can see that there is a perfect negative linear relation because the trend is going downwards and I can fit a perfect line there. So r there is going to be -1. The next one, E, I can see here that there is a trend going downwards and it's very strong trend. I can see it clearly. So this is a strong negative linear relation and r is about -0.9. The next picture is going to represent a moderate negative linear relation because I can still see a trend of the scatter plot going downwards. It's just not as strong as the previous one, so this is a moderate negative linear relation, and r is about -0.4. It could be less, it could be a little bit more. The next one, number G, I cannot see here any linear trends. The dots are all over the place. So we say here we don't have a linear relation and r is very close to 0. The next example, H, I cannot see any linear relation here, and r is going to be equal to 0 because the trend is not linear at all. It follows a curve. So this is definitely not a linear relationship. This is the previous example, and we want to compute the sample linear correlation coefficient for this drilling data. Remember that we previously graphed this data and it gave us this type of data. You will see that there is a positive trend going upwards. You can actually see that if you click on the plus sign and then just check the box that says trend line. You will see that there is a line here going upwards, so that means there is a linear relationship here. It happens to be a strong linear relationship, so I'm expecting r, when we compute it, to be very close to 1. It has to be in the range of 0.9, 0.8, something like this. So I will show you how to find the sample linear correlation coefficient, r, using Excel, and I will show you how to do it following the formula that I introduced you with. I just want to make sure that you understand that we're not going to use the formula, we're going to use Excel. So here is the trend. I graphed the data already and I put the trend line there. You don't need to do that, but it's nice to see it. The line actually clearly fits the data. The next step, you're going to click on the plus sign again, and you're going to go to the trend line and click on the more options at the bottom. So you can see it actually here. So let me just make it a little bit smaller. So click on the trend line, go to the arrow and click more options. You want to make sure that the linear is selected, and you're going to scroll down. So you're going to display the R, which is this option right here. As you can see, it showed you R. Right here you can see it clearly, but this is squared, so it is your duty to determine r. We have r squared, so r, we're going to take the square root, so this is equal to sqrt of 0.5973. So this is the correlation coefficient. Excel always going to give you a positive answer. It is your duty to determine whether it is positive or negative. How do you do that? You're going to look at the trend line. If the trend line is going upwards, if you scan it from left to right, then R is going to be positive for sure. If the trend line is going downwards, then R is going to be negative. But this number is always going to be positive if you compute it using Excel. So do not rely on Excel to tell you if R is negative or positive. This is something that you have to determine yourself. So that is how we're going to compute R using Excel. Now, to use the formula, we're going to follow all of these steps. First, we need to compute the mean and the standard deviation for the variables, both of them, X and Y. Then we're going to follow the formula exactly here. So let me show you. So here is my data. All I did is just I copied this and pasted it in Excel, resized it a little bit. The first step is to find the mean and the standard deviation for each of these variables. So I'm going to say average of the X values, click enter, and then I will take the same formula and drag it to the side to compute it for the Y value. Same for the standard deviation, ST, and then I will choose the sample standard deviation for the X values, and I will drag it over to compute it for the Y values as well. So those are the numbers at the bottom that you see right here. This is how we computed them. Let's continue. Now, the next step, we want to compute each of these X values. We're going to subtract the mean from it and divide by the standard deviation. So this is going to be equal to, open parentheses, because Excel doesn't understand the priority of operations, or it doesn't understand PEMDAS in general. We want to see X minus the mean. I'm going to click on this cell because the number is a little bit big for me. I am going to Fn, F4 to lock it in place, and then I will divide with the standard deviation. Again, the number is big, so I'm just going to lock it in place, click in Fn, F4, and click enter. Now that did it for me, so I'm going to do the rest of the table in the same manner. Now, I will do the same for the y value. So I'm going to say, click on the y value. Don't lock this value. Sorry, open parentheses first. And then click on the y value. Don't lock it. Minus the mean, which is this number. Since it's a single number, I'm going to lock it in place. Close the parentheses and divide by the standard deviation. It's one number, so I'm going to lock it in place as well. Click enter, and then I'm going to populate this right here. The next step in the formula says that we need to multiply these two columns together. And now we just need to add it up. So we're going to say sum of the last column. Now, this is just the sum. Remember, the formula says we need to divide by n minus 1. So we just did all of these steps and we found the total number. As you can see, it's the same number. Now we want to find the final answer by dividing by n minus 1. We have 12 values, so we're going to divide the number by 11. So the last step is just take this number and divide it by 11. So this number divided by 12 minus 1 is 11. So this is the correlation coefficient. We got the same answer when we used Excel, so we don't need to memorize the formula or how to do the formula, because we're not going to ever use the formula to compute the correlation coefficient. We're going to use Excel. We're going to use the scatter diagram and then draw the trend line and display R square and display the equation on the line. Testing for a linear relation. First step is to determine the absolute value of the correlation coefficient, meaning we're going to only look at the positive value of R. The next step is to find the critical value in the table that I'm going to show you in a minute for the given sample size. And then you're going to, if the absolute value of the correlation coefficient is greater than the critical value, we say a linear relation exists between the two variables, otherwise no linear relation exists. The table that I'm talking about is this table. This is the critical values for correlation coefficients. So if we want to determine whether a linear relationship exists between the two variables that we studied before, which is the time to drill 5 feet and the depth at which the drilling begins, and we want to comment on the type of relation that appears to exist between the time to drill 5 feet and the depth of which the drilling begins. As you can see, we computed the correlation coefficient between the two variables, and it happens to be 0.773 approximately. The critical value, this is the absolute value, of course. It was positive, but the absolute value is going to make it for sure positive, even if it was negative to begin with. The critical value, as you can see, our sample size was 12. So we're going to look at this critical value right here. Since the critical value is 0.576 is less than the correlation coefficient, we're going to say there is a positive linear relation between time to drill 5 feet and the depth at which the drilling begins. So this is how we're going to use this table. According to a data obtained from Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.94 or 940. Does this mean that a higher percentage of females with a bachelor's degree causes a higher percentage of births to unmarried mothers? Certainly not. The correlation exists only because percentages have been increasing since 1990s. It is this relation that causes the high correlation. In general, time series data collected over time may have high correlations because each variable is moving in a specific direction over time. Both are going up or going down over time, one increasing while the other decreasing over time. When data are observational, we cannot claim a causal relation exists between two variables. We can only claim causality when the data are collected through a designed experiment. Another way that two variables can be related even though there is not a causal relation is through a lurking variable. A lurking variable is related to both explanatory variable and a response variable. Here's an example. Ice cream sales and crime rates have a very high correlation. Does this mean that the local governments should shut down all ice cream shops? Of course not. The lurking variable is the temperature. As air temperature rises, both ice cream sales and crime rates rise. So here is another example for lurking variables in a study that is done to determine whether cola affects the bone mineral density. Because colas tend to replace healthier beverages and colas contain caffeine and phosphoric acid, researchers Catherine L. Tucker and associates wanted to know whether cola consumption is associated with lower bone mineral density in women. The table to the right lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. The data were collected through a prospective cohort study. The figure on the next page that I will show you in a minute shows the scatter diagram for the data. The correlation between the number of colas per week and the bone mineral density is negative 0.806. The critical value of the correlation with n is equal to 15 from the table that I showed you previously is 0.514, and because the absolute value of the correlation coefficient is greater than the critical value, we conclude a negative linear relation exists between the number of colas consumed and the bone mineral density. Can the authors conclude that an increase in the number of colas consumed caused a decrease in the bone mineral density? Let's identify some lurking variables in this study and see if that is the case. So this is the scatter diagram of the previous data. In a prospective cohort study, data are collected on a group of subjects through questionnaires and surveys over time. Therefore, the data are observational. So the researchers cannot claim that increased cola consumption causes a decrease in bone mineral density. Here are some lurking variables in the study. The first variable could be the body mass index. It could be the height, smoking, alcohol consumption, calcium intake, physical activities, and more. You can count many other lurking variables in this study that is going to affect the result of the study, and therefore the researchers cannot claim causation. The authors were careful to say that increased cola consumption is associated with lower bone mineral density because the potential lurking variables. They never stated that increased cola consumption causes lower bone mineral density. Just like we learned before, we can never claim causation if we are using an observational study. We can only claim association. The least square regression line. So now that we could see the relationship, the strength of the relationship between two variables, can we create a line that is going to estimate the relation and give us a chance to predict future values? This is what we call the least square regression line. We're going to find the least square regression line and use it to make some predictions. Interpret the slope and the y-intercept of the least square regression line. We want to compute the sum of the squared residuals. If we have the following data, we have x and y, and we want to find a linear equation that connects the two variables together. If we follow an algebraic approach, we're going to pick 2 points, we're going to find the slope, and then we're going to use the slope point formula in order to find the line. We're not going to follow an algebraic approach, we're going to follow a different approach. Then we can graph the equation on the scatter diagram. As you can see, it doesn't fit exactly all of the dots, but it is a good fit for the data set provided for us, because the distance between the line and each of these dots is as minimum as possible. And then we can use this equation to predict when x is equal to 3. So we just plug it into the equation instead of x and compute, so we get 4.75. So the value of y is going to be 4.75 when x is equal to 3, and this is a prediction using the equation that we computed in the previous step. The difference between the observed value of y and the predicted value of y is what we call the residual or the error. So the residual, as you can see in the picture here, is the distance between the actual value and the observed value, which is the actual value, and the predicted value, which is the value we found using the equation we created in the previous steps. So the residual is going to be the observed y, which is going to come from the raw data we have, minus the predicted value of y, which is we computed in the previous slide by plugging 3 into the equation and solving. So we got 4.75. The residual in this case is 0.45. Notice how the residual is positive in this case because the data value is above the line. The least square regression line is the line that minimizes the sum of the squared errors or residuals. This line minimizes the sum of the square vertical distance between the observed value y and those predicted values by the line y hat. The equation of the least square regression line is given by y equals bx b1x plus b naught. b1 is r times s sub y divided by s sub x, which is the slope of the least square regression line, and b naught, which is the y-intercept, is computed using y bar minus b1 times x bar, which is also called, this is called the y-intercept of the least square regression line. X bar is the sample mean and S sub x is the sample standard deviation of the explanatory variable x. Y bar is the sample mean and S sub y is the sample standard deviation of the response variable y. Let's find the least square regression line for this set of data, and then we're going to use the line to predict the drilling time if drilling starts at 130 feet. Of course, it is here. That is the actual value, the observed value. But we want to use the line that we create in order to predict that. If the observed drilling time is 130 feet above or below average, is it above or below average? We need to determine that by seeing the residual. If the residual is positive, it's going to be above average. If it's negative, then it's going to be below average. We want to draw the least square regression line on a scatter diagram of the data. So here is Excel. I just copied and pasted the data here. I am going to create this scatter diagram for the data. So select the data, and then you're going to go to the Insert tab, and you're going to go to the scatter diagram and select the scatter diagram. The next step is to click on the plus sign and go show the line. So I already graphed the least square regression line on the scatter diagram using Excel. Then click on the arrow next to trend line and select more options. Here, as you can see, you're going to select display the equation and display the R square. That is the option that you'll see. If you do that, you'll see that you have an equation and you have the R square. The R square, you can find R by finding the square root of the number given. We computed that previously. It was about 0.773. So this is R. The equation, as you can see, it is y equals to 0.0116x plus 5.5273. So this is least square regression line equation. As you can see, it's the same here. Now, we need to find the predicted value for 130. We know the observed value for 130 is this value right here. So I'm just going to highlight this. We need the observed value for 130. That means when x is equal to 130, what is y going to be equal to? So that is equal to, I'm going to use the equation. So 0.0116 times, I'm going to remove x and plug in the value of 130, which is the x value, plus 5.5273. I'm looking at the equation and I'm typing it as I see it. Enter. This is the predicted value and this is the observed value. Now, the residual is observed value minus predicted value is equal to observed value minus predicted value. So as you can see, the residual is negative. What does this mean? That means the observed value is below average. So we're going to say that because the observed value or the observed drilling time is less than the predicted drilling time, when we find the residual, we found that the residual is negative. That means the drilling time of 6.93, which is the observed time, is actually below average. Now, we have a slope in our equation, as you saw here. The number in front of x is what we call the slope. So the number 0.0116 is what we call the slope. The number 5.5273 is what we call the y-intercept. We have an interpretation for the slope, and sometimes we have an interpretation for the y-intercept as well. The slope for the regression line we computed was 0.0116. That means for each additional foot of depth we start drilling, the time to drill 5 feet increases by that amount of minutes, so 0.0116 minutes on average. So you're going to use the context of the question in order to interpret the slope. Since the slope is positive, that means I know that when the explanatory variable increases, the response variable is going to increase as well. The explanatory variable is the feet, how many feet we start drilling at. So as that distance increases or the depth increases, I'm expecting the y value, which represents the time it takes to drill 5 feet, to increase. So this is exactly how we're going to interpret the slope, depending on whether the slope is positive or negative, and it has to go with the context of the question. Sometimes we are able to interpret the y-intercept only in 2 conditions. The conditions that we need to meet first, or the questions that we need to answer first before we are able to interpret the y-intercept, are: is 0 a reasonable value for the explanatory variable? So let's plug that into the context of the question. If x is equal to 0, that means we're going to start drilling at the surface of the earth. And that makes sense. We can definitely do that. So 0 has a meaning in the context, and it represents something. Do any observations near x equals 0 exist in the data set? Let's look at our data set and see. Yes. So 35 feet is very close to the surface of the earth, and I have an observation already related to that. So yes, that is the case. So we can definitely interpret the y-intercept. So how do we interpret the y-intercept? The y-intercept in this context is the time it takes to drill 5 feet from a certain point. And when we interpret the y-intercept, it just means that we plug x is equal to 0. So as if we start drilling at the surface of the earth. So how many minutes we expect that to take? We expect that drilling 5 feet from the surface of the earth to take 5,5273 minutes. And that is how we're going to interpret the y-intercept based on the context of the question itself. Now, be careful when you interpret the y-intercept, because not always you're going to see a nice interpretation for the y-intercept. Sometimes that doesn't make any sense at all to interpret the y-intercept. So keep that in mind. If the least square regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, we say that the researcher is working outside of the scope of the model. Never use a least square regression line to make predictions outside of the scope of the model, because we cannot be sure the linear relation continues to exist. We're going to end the video with this caution. So I hope this video helped you understand the relation between 2 variables, the explanatory variable and the response variable. We're going to create a project based on this, so make sure that you ask plenty of questions if you do have any questions.